All right, so this is Computer Science 305 programming languages, and today we're going to be talking about the basics of polymorphism and how it appears inside of different programming languages. And so the basic concept is, we need to actually think about this from the context of a programming language that we've been exploring, and so we're going to look at ML. And so we want to first take a look at the different types that we have, for example, here, right? So the ML function is very flexible, right, since it can be applied to any pair of the same equality testable types, right? So if you look at this down here at ML, our function f of AB, where where the test is a equals b, right? It gives us the double apostrophe a by the double apostrophe a. So two unknown types that are equality testable and returns a Boolean, right? Versus if we look at the C version of the same function, right? But it takes in char A, char B, and then checks if they're equal, right? The ML function, as it says here, is much more flexible than the C function, because it can take in any types as long as they're equality testable. So, for example, it cannot take in real. But so polymorphism is really essentially functions that, in the case of the language that we're talking about so far, are functions with extra flexibility, or with this type of extra flexibility, are called polymorphic. But polymorphism or polymorphic is quite difficult to define, right? Because it applies to a significant number of language features. It could be functions, variables, objects, all sorts of different things that are part of languages. And then various languages have different levels of polymorphism, or different implementations of polymorphism. And so we're going to explore four major examples and then return to the problem of finding a definition that covers them. So basically, the things that we're going to talk about are the concept of overloading, parameter coercion, parametric polymorphism, subtype polymorphism, and then we'll come back and redefine them. So the four types we're talking about are the first four items here, and then we're going to try to figure out how we can classify this. So first concept, overloading, right? An overload function name or operator is one that has at least two definitions. So, for example, think about the plus operator in most languages are overloaded to have the capability to, for example, do string concatenation, so it can take in two strings, or the capability to take in a string and something else for string concatenation, which then goes into coercion. But plus by itself, when we're just thinking about addition, can handle integers, reals. In Java, we can. It allows us to essentially coerce variables to be of different types, so that it can be applied. So, in some languages, Java, Ruby, ML allows us to actually have the capability to overload function names and operators with new definitions. And so, for example, there are some predefined overload operators in ML, right? Which is like, as I was talking about, the plus, right? So in the ML description shown here, you have the value, the variable x and y, and so x is showing us that we have the addition of two integer types, and then y is the addition of two real types, right? It's the same operator, it's just redefined or overloaded in this case to handle two different types. Pascal, on the other hand, right, we're using it a little bit closer to what I was talking about earlier. In Pascal, we can use it to, it's been overloaded to handle integers, real numbers, strings, and apparently arrays as well of characters. So awesome. So you can add overload operators. So the term operator means, in this case, like things like the plus, less than, minus, divide, multiplication, all these operator terminals in the grammar that can be redefined in languages like C++, Scala, Groovy, C# can do some. but you have this ability to redefine them for new types that you've created. So for example, in the C++ example here, we're creating a complex number type, and what it has is it has a real part and an imaginary part. And then what we want to be able to do is we need to override the operator for plus and multiplication to be able to handle the correct modification for a given real number, or for a imaginary number. And so what we do is we create this this complex this operator, right? It's a friend of complex, and gives us the capability to override what it's going to do. So it has the ability to take in two complex numbers and returns a new complex number, both for plus and for multiply. And then we have another function down here that just is utilizing them, showing us that it can actually do this. So in C++, we can actually override pretty much any operator that exists, which includes the capability to dereference and reference, dereference pointers, subscripting for arrays, function calls, allocation and deallocation with the new and delete operators. So basically pretty much everything could be overloaded in C++. Not all languages are quite as permissive as this. For example, in Java you cannot overload any operator, so enjoy that. You can also overload function names in C++ and a significant number of other languages, right? You can allow them, you can define a variation of the same function that takes in different types for parameters and has a different return type but the same name. Now this gives us the ability to have more flexibility, but it also makes it more complicated in understanding which one do we pick. And so in order to eliminate overloading, right, that problem where you have to have you have to try to figure this out, what the compiler will do is it goes through and renames the overloading such that you can have essentially square I square D as opposed to two different variations of the same name square, right? And then it goes and rewrites those inside of where they're actually used. You can do this manually if you want, to probably make it so it's a little easier to understand what's going on, but at the same time you lose that capability for overloading. But as we can see here, if you can do this, it's equivalent to the same thing. It's just, you know, now you have specific functions for these specific types. Compilers, like I said, typically can implement overloading in the same way. You can write overloaded overload functions in your code, but the compiler goes through and changes their names, basically creating a set of what they call monomorphic functions, one for each possible definition, right? And then creates a mangled name for each, encoding the type information. So that gives us the capability to then it goes and rewrites all the uses of those to their appropriate mangled name, which is depending on those parameter types, right? So if you're in Java and you create an overload function where you have one function that takes in one version takes in 3 strings, and the second version that you have takes also in 3 strings, Java won't be able to determine which one that is, regardless of the return type. So you actually have to have, it's very highly dependent on what they call the method signature in Java and C++. So for example, one more C++ implementation, right? So we have two overloaded versions of the Shazam function. When these are actually converted to assembler, right, through the compiler, what it's going to do is it creates one called Shazam FII, right? So it's the first function, and II is the type information of the parameters, right? And the second one is Shazam FDD, which is using, because you have 2 doubles coming in, so that gives us the new version of that. It's just one way of handling this type of thing. There are other languages that allow you to have overloads that have the exact same basic method signature and allow you to have different implementations, then it becomes very difficult for the compiler to handle that. Alright, so this is the first part is over, and the second part will begin at parameter coercion.